Friday Astronomy. We're going to have Dr. Alejandro Soto here talking about dust storms on Mars. Join us on August 5th for Dr. Katie Devine from College of Idaho, who's going to talk about star formation. I'm going to turn it over to Dr. Alejandro Soto now.
All right, thank you very much. Glad to be here. All right. Okay, so I think we got all the technical stuff done. Glad to be here. Hi, everyone. Again, my name is Alejandro Soto, and I'm going to talk to you today about dust storms on Mars. So hopefully that is something that you walk away from this kind of excited about this different world. And one of the things that I get excited about it, which is this great sort of storm systems that we get on Mars. So Mars is a fascinating place to me. It's smaller than Earth. So this is two images where I'm trying to show the scale. Basically, you can think about it, Mars is roughly the size of the Earth's core. But I think the picture is a better way to compare it, because how many of you know the size of the Earth's core? I don't remember the size of the Earth's core. But even though it's much smaller, it has a thinner atmosphere. So the atmosphere on Mars is like the equivalent in terms of atmospheric density as being up in the stratosphere on Earth. So, way above where airplanes fly. So it has this thin atmosphere, but despite those differences, it still has a complex and exciting climate. It's a different one than Earth, but still, in my opinion, exciting. The atmosphere is primarily made of carbon dioxide, 95% of that, and then a little bit of nitrogen, argon, and water vapor and some other stuff, but it's mostly CO2. And then it's, let me think. I was gonna say, right now we're breathing 1 bar of atmosphere. Mars has an average of 6 millibars, so it's 1,000 times less. That's another way to think about it. But despite those differences, we get some of the same features on Mars. It has wind. It has frontal systems, like if you're listening to your weatherman talk about, we got a storm front come in, a low pressure front, a high pressure front. It has all those things. And it has storms. It's just the storms on Mars are dust storms. There's not enough water vapor on Mars. There's water vapor in the polar caps. Let me turn on this little fancy little laser thing here. There's water vapor in the polar caps, both in the north and the south. And then some of this white stuff is water vapor clouds. So water ice in the caps, water vapor clouds. There is a little bit of water moving around, but it's not a lot at all. So you don't get like wet storms like we do. There's no rainfall or precipitation on Mars currently, but you do get dust storms. So if you've ever encountered a dust storm in the southwest of the US, or if you've been to some more farther away places like the Middle East or North Africa or the Gobi Desert in Asia, or even weirdly Iceland, which gets dust storms sometimes, those are the kind of storms you see on Mars. And that's what I want to talk about today. I wanted to start a little bit with a short history of Martian dust storms, because it turns out we've been observing these for quite a while. Dust clouds and storms have been observed on Mars as far back as the 1870s. When a scientist by the name of Antoniadi, an Italian observer, is usually credited with the first observation of dust clouds, although he described them as yellow clouds, because he was using one of these old telescopes, what they call refracting telescopes. So it's sort of the type you think of like a pirate holding up or something, but bigger. And he was just looking through it with his eyes and making observations. They didn't have any way of imaging back then. So they would just make drawings, make observations. And with the resolution they had with those telescopes, there was 3 types of clouds that we would usually see: white, blue, and yellow. And we've worked out historically that the white and blue ones were really water vapor clouds, and they were rare, but they kept seeing all these yellow clouds all over the place. And even eventually by 1894, one of them was being identified, the S here in this really not so welcoming name for classification. The S signifies that they thought it was a storm because they actually saw the cloud moving while they were observing it. So we've known about that there was something going on, and people were early on guessing that this might be dust storms, all the way back well over 150 years ago now, right? So that's kind of exciting, but we went a long time without making a lot of progress in understanding these things. I only showed a little bit of this table here from a paper. It goes on for like 2 pages, and there's observations like almost every year of either local storms, and usually every few years you get global dust storms, all the way up into the 1970s. And in the 1970s, something changes at that point, which is kind of exciting. This is a sequence of images of a dust storm, a global dust storm from 1971. The reference on there is 1974 because that's when the paper was published, but the storm actually took place in 1971. And I wanted to show this one because it's a transition sort of in the history. These are still ground-based telescope observations. So we've improved at least. We can take images in the 1970s from the ground, although these were probably still photographic plates as opposed to digital images. A group called the International Planetary Patrol, which I love that as a name, they were busy back then regularly observing all the planets that they could. They had a suite of telescopes scattered around the world so that hopefully one of the telescopes on any given night could observe some interesting stuff. And so I don't know which telescopes each of these images goes with because it wasn't detailed in the paper, but this is from that program in the early 70s. And so the way to interpret this here is an image where there's no dust storms. So this is what Mars used to look like when you looked at it from a telescope. This is what people knew about Mars in the early 70s. And you see all these, the technical term is albedo features, but they're really just brightness and darkness features is the easier term for it. And a lot of these features were stuck in time. Like the observers knew it, they saw it every time they went to look at Mars. So this is their like normal case, right? But what they observed after August, so starting in September of 1971, they started observing that a lot of these features they were used to seeing started disappearing and started getting obscured and fuzzy. And what's going on is that first a regional, you can't tell where in these images, but we know now in all likelihood a regional dust storm started forming, and that dust storm grew so big that it was a dust storm that covered the entire planet. So you finally get to this bottom sequences of images where you see this is the same sort of observational setup, same filters and everything else. But now here in the bottom right, by October 14th, you can no longer see the surface of Mars anymore because this dust storm has just covered everything. And I said, this is the transition point, because the reason this is the transition point is this is also the same time that Mariner 9, which is one of the US missions to Mars, arrived at Mars. This is the first mission to go in orbit around another planet. And they were all excited. I mean, I've talked to some of these guys when I used to work at JPL, there were still some of them around. They were all excited to go work on this. They were going to arrive, they were going to go in orbit, and they were going to start taking images. Instead, what happened, they arrived, they got in orbit, they took an image, and they couldn't see anything because it was all completely obscured. And because of the resources they had back then, they had to actually delay, sort of put the spacecraft into sort of sleep mode for like a half a year or so and wait till the storm go away before they could actually start their mission. And I don't know the details of this, but I will mention, I think the Russians actually lost a mission to this dust storm because the Russians had a lander. They were in a race with us, because that's what we used to do back then. I shouldn't say even Russians, it was the Soviets back then. They were in a race to us. We were going to get in orbit. They were going to beat us by landing. So they landed in the middle of this dust storm and lost their spacecraft, which is actually what usually happens when you try to land on Mars, based on the track record. So this is that big transition where we're going to move away from depending on ground-based telescopes with this kind of resolution to spacecraft. Spacecraft get in orbit. So I don't have any Mariner mission images, but we did get some from Mariner that were a lot better than what I just showed you. But I just had to skip ahead to the really good stuff. And so by the late 1990s, early 2000s, we had a mission called the Mars Global Surveyor. It was in orbit around Mars. It had a camera on there called the Mars Orbiting Camera. Sometimes we are not the most original people in naming things. And it had the ability to look at narrowly like a telephoto lens and looking close, but also had a wide angle lens so it could stitch together complete globe pictures of Mars. And that's what we're looking at here. Let me move that stupid laser pointer out of the way, right? So this is, I'm going to show you two images. I'm going to show you the first one right now. This is from 2001. It's before a dust storm shows up. And so this is like the image before that was in the top left, a so-called normal image. This is normal Mars, right? It's kind of fascinating. We can see craters now in this type of images. We can see we still have those light and dark features. And over the last few decades, we've been learning the different compositions that make that up. I'm just trying to see if there's anything other. You can't really see Valles Marineris in here or any of the big stuff. But the interesting thing is this down here is a giant impact crater basin called Hellus Basin. except it probably doesn't look so impact crater basin. It doesn't look like a hole to you probably. And the reason is this is actually filled with a regional dust storm right now. That's why it's so bright. It doesn't look like an indentation like this crater over here, because there's a regional dust storm here. And you can see that over the polar caps, there's a little bit of yellow and brown. And that's because dust has been depositing on the polar caps as well. But so this is late June 2001. In this image, we got that seasonal dust storm going on, but there's the regional dust storm. But just a month later, boom, global dust storm, right? Now we've had the same thing happen again. So this is what I find exciting about Mars, is that like it has storms, but it has storms that we don't even have. We don't have anything like a global storm at all, right? So we're trying to understand why we get global dust storms on Mars, what controls them, what decides when you get them, because you don't get them every year. But they're kind of fascinating because they really do fill up the sky like this. Like the features you see is just a little bit of the South Polar Cap down here, and you can probably convince yourself you can see this region over here if you really want to. But no, it's the skies there are filled. If you were on the surface, it would be dark during the day because there's so much dust in the air. So I want to walk through types of Martian dust storms because one, it'd be good for you guys to see what they look like, and two, because it gives me a chance to show more pretty pictures, and who doesn't like that? So again, I'm going to go back now to this video that was showing before we started. This is a different global dust storm. This is not 2001 now, this is 2018. And I wanted to show this one as well to show that we're still getting these high resolution images from our spacecraft. But you look at the dust storm picture on the right, and it looks a lot like that 2001. Like every time we look at Mars when there's a global dust storm, it really washes everything out and it starts looking the same after a while. All right. But besides global dust storms, we also have regional dust storms. So here's an image taken by the Mars Global Surveyor back in 2002. This is early northern spring. So what's happening is over northern winter, this ice cap grew. You deposited water ice. You deposited CO2 ice, actually. The CO2 in the atmosphere actually freezes out a little bit throughout the year. So you had this ice cap had grown. But over time, now we're heading into spring for the north. The sun's coming up. It's heating up the surface. That heating up is generating winds. The winds are picking up dust and moving it around. And then so we get these dust storms here. So this is a regional dust storm. This is a frontal system. If you follow it, I'm not good with this laser pointer, down this way and down this way. If this was a meteorologist talking about it on your 6 o'clock news, they would have one of those little lines with the triangles and the hemispheres and say, this is the frontal system. That's what this is here. And you can see the sharp line with all this dust activity going on. What I love is there's a lot of structure in there too. Like it's a big frontal system, but there's also a lot of little details going on as well. This is another North Polar storm. And so if you think of it, we're looking at this right now from this view. And if you imagine that from this view, we flew farther towards the North Pole. So we're more above the North Pole. That's what this image is. So here's that North Pole right here. And here's this other storm coming off of it. With this wonderful swirl pattern, just like we see in storms on Earth in the upper latitudes. You see these these little swirls on it. So this is another lovely one. This curling that we see, and this is, I should say, I apologize. This is a sequence of images. I believe it's every 2 hours-ish. So you can see that there's some evolving of the storm. This little simple curl breaks up and has little two pieces coming off of it. So we see rich dynamics at work. And the curling's of interest because what's going on is this is indicating there's a vortex that's following the storm. So there's this air spinning around the pole. And I know by now through the news, we've all heard about a polar vortex. That's what this is. And that's sort of driving the evolution of this storm. And we also know from looking at the storm that there's a certain amount of wind speed they must have had in order to lift the dust and generate these storms, which I'll talk about more later about how that's done or how we think it's done, because we don't really have full answers. Let's see, what else do I want to say about this? Yeah, I think I covered everything I wanted to say. Oh, no, I won't. A couple more interesting things about this. These storms arise because I said we're heading into spring. The winter CO2 cap starts to sublimate. It doesn't go through a liquid phase. It goes straight from ice to gas. So that's sublimation. And what this means is now we get suddenly this burst of atmospheric pressure right over the cap. So that's also driving dust away from that North Polar caps. Is what you get is a high pressure system that's driving this. Then you also have a temperature contrast between the cold ice and the warmer land over here, and that often drives winds as well. And then also the act of sublimating, of removing some of that CO2 ice, turning it into vapor and moving it away, also drives the circulation. So this is actually a very complex circulation here that's generating these storms. And this is still an active area of research where we're trying to figure out what is going on with these things. This I love a lot. This is where I'd like to compare a dust storm on Mars to a dust storm on Earth, because one of the cool things is for all the differences I described, there are similarities, right? So on the left, it's a Martian North Polar dust storm. So I believe this is the North Polar cap here, right? And so coming off this cap is this frontal system right here. And it's moving out with like a central jet right through here, and then it mushrooms out, and we have these little vortices spinning off that jet, right? And it's being driven again because of that winter frost is now sublimating and pumping CO2 into the atmosphere. But we get the same effect here. So this is an image from a mission called CWIFS that orbits Earth. And this is Northwest Africa. You can see the coast of Africa right over here. And so this is dust from the Sahara Desert. But once again, a frontal system coming off of Africa is driving this, driving a central jet that's pumping all this dust out into the North Atlantic, but creating the same type of features, right? And what's also interesting to point out is that the images are the same scale. They both have 4 kilometers per pixel. You can't see a pixel here, but if you imagine a tiny little box down here, it's 4 kilometers. But basically the size of this storm on Earth is basically the same size that we're seeing on Mars. So, which is really kind of cool as well, that we get the same phenomena and we get the same scale as well. I also wanted to point out that as you zoom in, the pictures get fuzzier because of the edge of resolution, but this is what I mentioned earlier, that these storms have a lot of structure. These are all, so you have the larger, bigger storm, but within it, you have all these different clouds. You have this cloud streaking, and I'll be honest, I don't know why these are streaking, and I have to go dig deep. Maybe no one knows yet. We have a lot of these images that we still need to work through and understand what's going on. But clearly there's a lot of detailed physics that are going on here that's kind of exciting, that we really want to understand as we go forward, because I've already shown that there's some connection to Earth. We get dust storms on Earth, get dust storms on Mars. Do they function the same? Do they work the same? Does studying Mars dust storms help us understand Earth? I think so. So that's what we're going to continue studying these. This is a mosaic now. And this happens to be a mosaic of multiple days, but what I just wanted to show you is there's a lot of gaps. So all these black areas are gaps where the spacecraft wasn't able to get an image. And the reason for this is because this is an image from, this is a mosaic of images from the Mars Reconnaissance Orbiter, which I actually worked on as an engineer back in 2003, 2004. And one of the challenges we had with this is a really great spacecraft. It's got a lot of great instruments on it. It's got this instrument called HiRISE that does high resolution imaging. It sees like 20 centimeter objects on the surface of Mars, which is really cool. But it also has a wide angle camera called MARCI that's trying to take these swath images and get a global picture of Mars like once a day or once every few days. The problem, as you can imagine, is that these guys compete. The high-res camera likes to look sideways sometimes and look back and sideways and trying to make stereo images. And every time it does that, the wide-angle camera team gets angry because it puts these gaps here. So that's why we have these gaps. And this is one of the challenges of doing this kind of research, is that you have a bunch of scientists who want to do different things. All the science is cool, and you have to manage who sort of gets the priority at any given time. So I've shown you some images. The 2018 storm was from the MRO mission. There was no gaps in that image where the orb was rotating. And that's because that was probably a sequence of images that the Marcy team sort of, you could say in air quotes, won out. And this is probably a sequence of images where we were prioritizing the high-rise images. And yet, despite the gaps, we still see some cool things. So this is over here is Olympus Mons, the tallest volcano in the solar system. Tharsis Montes is a series of volcanoes right here. Valles Marineris, if you've ever learned about Mars, you probably heard about it. It's the deepest canyon in the solar system. So I'm just giving you some context. Now we get down here, and this is the South Polar Cap. And what I love this image shows is all these storms coming off the South Polar Cap. So this time we're at southern spring, not northern spring, but it's the same physics going on. This time it's the southern polar cap that is sublimating, turning the ice into vapor, pumping it into the air, and in doing so, it picks up and moves around dust and creates these regional dust storms, which are just beautiful. And these storms are now starting to interact with the topography. Some of them will dive into craters. Some of them will move north. Some of them will just dissipate and disappear. Though the other thing to note is there's so much dust being pumped into the atmosphere in these type of storms that even other regions over here, like Valles Marineris, for example, has this like bluish hue to it. A lot of that is actually because dust is already getting pumped from here all the way up to there, and it's haze, basically. It's not enough dust to be qualified as a storm. It doesn't have cloud features, but it's like a hazy day. I don't know how often you guys get hazy days in Boise, but out in the Great Plains on the Front Range in Colorado, we definitely have our days where you can see the dust and haze get lifted up off the agricultural farms and just basically sort of model out and blur out the sun for the day. And that's what's happening all over Mars, even though the storms in this case are isolated. So the big challenge is, how do dust storms form, right? This is an area that is an active area of research. So I'm going to talk about some ideas, but really we don't know what the definitive answer is. But we're working on it, and we're hoping to send more missions to Mars that would actually try to tackle this question in detail. But to understand storms, how these storms form, you got to go down to the surface. This is one of the cool things about studying Martian dust storms is, as an atmospheric scientist, this is also an excuse to work with the geologists, and because it's all about that interface between the surface and the atmosphere. And so what I have here are 4 images from the Mars Opportunity rover that was launched in the 2000s and survived into the 2010s before a dust storm basically took it out. As you can see, the surface of Mars is rough, it's rocky, it's covered in sand and dunes and volcanic rock. But all over these features here, and it's not obvious necessarily, but all these features, the sand, the platform for the spacecraft, they're actually all covered in dust. Dust is everywhere on this planet. It's why I like to say, like, Earth is a water world, Mars is a dust world. That's the dust on Mars is sort of the equivalent of what water is on Earth. So that helps. That's our number one thing we need to form dust storms. We need a source of dust. So we got that. That's good. That's a good start. But how do we get this dust off the surface into the air? If you've ever had to deal with dusty surfaces in a dry, non-human environment, you know that they get sticky. They get sparky because electrostatic forces, they cling to things, right? And it's even worse on Mars, right? So we need some mechanisms to get the dust off the surface, because otherwise it won't stick to the surface. So how do we get enough dust in the air to form dust storms? So there are 2 dominant ideas, and it's not clear if one is the answer or the other or some combo, or is there a third possibility? But I want to talk about these 2. One is something called saltation, which I'll explain in a second what that is, that leads to dust being lifted in the air. And the other one is dust devils. And I'll explain that one, but some of you might have actually seen dust devils, because I know we get them all throughout the West here on Earth. So saltation, what is it? What is it good for? I want this stupid thing to stay away. Okay. Saltation is a technical term for some sand particle. Now I want the laser pointer. Some sand particle comes flying through the air, hits the ground, and in that process, it knocks other things around. The initial sand particle might roll along in what we call creep along the surface. It might bounce again. And so saltation is that bounce. The salt here is from Latin, which is the word for to jump or hop. Like in Spanish, it would be saltar. But what matters for the dust lifting and dust storms is during that process, it actually will often eject dust particles, which are smaller than sand, into the air. And since the dust is smaller, it can get suspended in the air, picked up by the wind and move around. And then it builds up from there if you get enough dust injected into the air. So this is not just a crazy idea. Not only have we seen it in the field, but we can actually see it in a laboratory setting. So these are two videos. The second one will start in a second, from a wind tunnel at Kansas State University. And this is the zoomed out version. The one on the right is a zoomed in of the image on the left. And so what we're seeing in the image on the left is the wind is blowing from right to left. And you can, if you look carefully, you can see little particles rolling along the bottom, but clearly other particles are getting kicked up and tossed into the air. So if we looked at the zoomed in version on the right, it's really cool. You can see they're almost like, at this scale, they look like giant boulders bouncing around, but you can see some of them hit each other, some of them knock them off the ground. So we know that saltation does this. And most of what you're seeing here is sand getting knocked around, because it's hard to actually, in this kind of experiment, to detect the dust. But we have other experiments that also show that the dust gets kicked up like this. So this is gorgeous. We know that at least in a laboratory wind tunnel environment, we can generate saltation, and saltation can generate dust lifting. So it's a viable mechanism. But one of the questions you might have, though, is on Mars, though, is the wind even strong enough? You're like, hey, Alejandro, you said earlier the atmosphere is thinner there. It's like being in the stratosphere. Is the wind even strong enough to move the sand around to do this? Question. Yes, it is. So this is an image from I have it. I'm suspicious I have this labeled wrong, because that doesn't look like the Spirit rover. I don't think Spirit rover has an arm like that. I'm pretty sure this is the Mars Science Laboratory, otherwise known as Curiosity. But my mislabeled image aside, what's more interesting and exciting is what this is that these are two images taken 5 days apart. And what you're seeing is that the sand in the region is moving, which is just lovely, because knowing that it's moving, something's got to move it, the wind is moving it. That they often did these type of experiments, and they continue to do these type of experiments with the landed missions, where they, they've been driving around, seeing all sorts of cool things, and sometimes they just park it for a while, 5, 10, 15, 20 days. Sometimes they don't park it on purpose because something breaks, but often they park it on purpose. And my memory's a little short here, but I'm pretty sure this was one of the times where they did this on purpose to see if they could see sand moving. And so this is not the only time we've seen this, but it's an excellent example that we have all the conditions we need, that saltation is one way of possibly injecting dust into the atmosphere. What's also cool about this particular experiment is it sort of has a lineage to it. So on the left here, I have a picture of Ralph Bagnold. He's one of sort of like the early pioneers in the field of understanding sand dunes, how dust moves, how the whole concept of saltation. And he actually tried to do these same exact experiments in Gilf-Keber, which I do not know where that is, but it's in the Middle East. And he was successful. I don't have images of that he took the comparisons, but he was basically doing that same experiment that we're doing on the right with the rover on Mars, which is really kind of cool if you think about it, right? Like, we're recreating what we've done on Earth on another planet. Quick side note, if, I just forgot the name of it. There's an Academy Award-winning movie about, I don't remember that tidbit, so I won't tell you. He actually was involved, Bagnold was involved in the British escapades, you could say, in the Middle East in the 20s, 30s, and 40s. And so he actually shows up as a character in movies over the years at times, because he was involved in all the politics and everything else. But while he wasn't politicking and colonizing, he was actually doing some cool science. So the other way of doing this is to let dust devils lift up dust off the surface and inject them into the atmosphere. So I'm going to talk about dust devils, what I like to think of as the frenetic dancers of the desert. And I'll show you what they look like in a second, but to talk about the physics a little bit, we get dust devils on Earth, right? They're also sometimes called sun devils, which I believe is one of the Arizona college teams' nicknames because they get a lot of them down there. But we tend in our community to call them dust devils. What happens is the surface gets heated up by the sun. This works best on a flat area, but doesn't have to be completely flat. But you see this a lot in the desert where you get a lot of heating that heats up the surface, and the surface heats up faster than the air above it. So now you have the surface is re-radiates some heat into the air right near the surface. That air now warms up compared to the air above it. You get buoyancy, you get rising, right? Hot air rises. I feel like all our parents told us that as kids. So now we get this hot air rising. It creates a low pressure underneath it that sucks air in from the side. So that's what we're seeing here in this step 3. Air rushes it to fill in. And often, but not always, that air starts, when it comes rushing in, it creates a swirling pattern. And so we get a swirling pattern. This is similar to like tornadoes and water spouts. But in this case, it's not as destructive. It can be, but not as. But if this is happening out in the desert where there's a lot of dust available, in that process of sucking air in and driving it up into the air, it sucks up dust and you get a dust devil. And that dust devil will start moving around and start tilting. It can be fun to watch until it encounters cooler air flowing in that eventually shuts it off and kills it. So often that happens if it started on one type of surface and moves to a different type of surface where the heating is different and it just doesn't get enough heat to maintain the dust devil, it just dies out. So you're like, okay, Alejandro, that's cool and you have a cartoon and all, but what do these things actually look like? This is what they look like. So both of these images above and below, you'll see dust devils flying by and they're on a loop. So if you missed it, you have a second or third chance. So this is on Mars in 2005. This is the top one's from April 15th. You'll see him burst by again here. Yeah, right there he goes. And we did our best to get as many images as possible, but we don't have, this is not like a high def camera or anything, so you don't completely see the spinning. But we have other evidence that confirms that they are spinning like a little vortex, like dust devils on Earth. And there's another one over here. And it turns out there's a lot of these going on Mars. Not everywhere. The mission called InSight that's on Mars right now, that mission was sent to Mars to look for earthquakes. It's found them. It's really cool. It's a whole nother topic you should have someone come out and talk about. But that site on Mars, they've never seen a dust devil there. But most of the other places we've been to, we see dust devils. So we've seen dust devils in Columbia craters, in Mariani Planum, in Gale crater. We now see them in Jezero, with a number of places, and we can see them from orbit. It occurs to me, I forgot to put an image from orbit of one of these, but we definitely see them from orbit. So those are our two mechanisms for putting dust into the air. We're not sure of what the source is. We don't know which one it is, and we're still working on it, but those are our sort of working hypotheses right now. Then the other trick is once you get dust in the air, to get the dust storm, you just need to get enough dust in the air that it starts feeding on itself. It's what's called a positive feedback loop. You put more in, it sucks up more. And the way you do that is because when you put dust in the atmosphere, the dust warms up. It warms the atmosphere. The dust absorbs solar light and then re-radiates it in the wavelengths of heat. So it warms the atmosphere around it. So if you start putting dust near the surface, like I said, the surface probably warmed up in order to get the dust in the air, or you have saltation going on, either one. So dust devils or saltation, put it here. But if that air starts to warm up because of the dust, it starts to rise and it creates more favorable conditions again at the bottom to put more dust in the air. And it starts to rise, it creates more favorable conditions to put dust in the air. And you can see you get this positive feedback loop. And if you get all the right conditions right, and you might say, hey, Alejandro, what are those right conditions? I don't know yet. I'm working on it. But if you do get all the right conditions, you get a dust storm. And if you get the right extra awesome conditions, you get a global dust storm. So we're not quite sure the transition from regional storms to global dust storms, but it's something we're actively working on. And we're trying to use sort of more modern tools, and modeling tools that we have from Earth to try to tackle that problem. By the way, I show this cartoon on the right as well, but just to point out though, this is a very similar process in many ways with what happens with water vapor on Earth. When you start evaporating water vapor off the surface, the water vapor in the atmosphere also acts in a way to heat the atmosphere and create rising. And that's how you get these beautiful plumes sometimes out in the Great Plains of plumes of clouds rising up. So I just also wanted to point out that we have a couple of ideas of how you get dust in the atmosphere. We definitely have images of storms, so we know we get dust storms, but we also have observations like this one. So this is, I'll take a second to explain what's going on in this image, but the point of this, I want to get the point across first, is that this data here shows that not only do we get dust storms, but we also just get enhanced amounts of dust in the atmosphere. So what this is from the thermal emission spectrometer on the Mars Global Surveyor mission. So what this was is that this spectrometer looked in the infrared and basically looks at heat. So I said that the dust in the atmosphere heats the atmosphere. So basically it'll figure out where the atmosphere is being heated up by the dust. And what it's plotting is blue is very little dust and red is a lot of dust. The gray in the background is a black and white image of the surface of Mars. So it's just showing you the topography. You'll see that the area that's colored with the data will move around because of the nature of the orbit of the spacecraft and details about when they turned on and off the instrument. They don't always get coverage everywhere. But the point is, oh, don't tell me. Is this the one thing that didn't work? Oh no, here it is. The point is, what you'll see over time is that some regions will get bright yellow. Eventually we'll see bright red all over the place. What's going on here is dust storms are forming, but we're not actually seeing dust storms in this data. We're just seeing that everywhere you start seeing extra dust throughout the year. And then you have periods of time of the year when there's a lot less dust. Although I'll point out the amount of dust, when it's less dust on Earth, on Mars, it's still more dust than we get on Earth in the atmosphere. But then it'll go back through again. So we're going through time over here. This is probably a period of heavy dust storms, and that meant that there's extra dust everywhere. So we have all the pieces. We know we can lift the dust off the surface. We know we get a lot of dust in the atmosphere, and we know we get storms. And now we're just trying to put those pieces together, and that's an area of active research right now. At some point, I just started showing video because it's just cool to see these things. So this is another example here where when it loops around, it might not loop, it might not. What you're seeing here is a regional dust storm that grows to nearly global. So the orange is a dust storm that's marking out a dust storm. And it's doesn't become quite a global one, but it covers most of the planet. These are the two MER rovers. I don't remember which is which. One's Opportunity, one's Spirit. But one of them definitely gets pounded by this dust storm. And I'm going to talk about what that means. What does it mean to be there in the middle of a dust storm, right? So robotic and future human operations on a dusty world. So I'm explaining to you, we get a lot of dust, we get dust storms, but even when there's not a dust storm, there's just a lot of dust around, right? And these dust grains, they're peak, if you think of like, you collected all a whole bunch of dust together and you measured all their sizes. The most common size is around 1 micron, so tiny, but they get up to 30, 50 microns, they get a little bit smaller, but tiny, small, the kind of thing that gets stuck in everything, right? So that's one of the future problems that's the current problem for robotics, future problem for human beings. But there's also the idea of what if you get stuck in a dust storm? And this is an idea that other people have put out. For example, the guys who made the movie, The Martian. Will this work? Right. No audio, but this is an opening scene from The Martian, and they got the astronauts walking around. They got stuck in a dust storm. There's large particles flying all over the place. Things get ripped apart, bang into people, spacecraft get destroyed, you know, the whole thing, right? This is not quite realistic. These particles are way too big. A dust storm on Mars would be probably a lot more like if you took sandpaper and rubbed it all over your face. It's more like fine grit sandpaper flying all around. Also, Mars's atmosphere, I mentioned earlier, is super thin. A thinner atmosphere means it has less oomph. It has less momentum because it has less mass. So in all likelihood, it would not be ripping things off like that. The real problem would be is it would abrade everything and it would get into everything. And your problem will be for future astronauts is how do you keep the dust from getting inside the spacecraft, inside your habitat? Because once it's in there, it's going to be a mess. You're going to breathe it in. You don't want to breathe in fine grit stuff. This is an OSHA nightmare if you want to think about it that way. So this is a little bit a fanciful scenario, scary scenario. But what is a more realistic one we know happens is, and one thing they did get right in this video is look how dark it is. It's super dark. Yeah, that's a real problem, right? Go away, laser pointer. So we lost a mission because of this. After 15 years, rover was lost because a giant dust storm came along and it got so dark and Opportunity was run on solar panels and it couldn't get enough power. It shut itself off. And although we have developed techniques that the rovers, if they ever get enough power back to try to call home, if they turn back on, it never called home again. Because in all likelihood, not only did it lose power during the storm, enough dust was left on top of it that it just never got power again. So to give you an idea what that's like, though, let's look at this. This is from the 2007 regional dust storms. This is not even a global dust storm because it was a global dust storm that took out Opportunity. But even just from a regional dust storm, what we're looking at is 30 days from beginning to end, right? And this tau is just some fancy term to measure how much dust is in the atmosphere. When tau's low, not much dust. When tau's high, a ton of dust, right? So the number's going up. And what you're seeing is here, this is a visible camera image of a spot on Mars. So there's a rock over there, there's a bunch of pebbles, there's the horizon, and there's the sky. And you can see over 30 days, while in the middle of this storm, how much darker it gets. This is probably the biggest risk for our spacecraft right now that are solar powered, which is most of them, is that in the middle of the dust storm, we're just going to lose all our power. We do have two spacecraft right now, Curiosity and Perseverance, that are powered by what are called radiothermal isotope generators. So they're little bits of plutonium. The plutonium decays. When it decays, it gives off heat. And that heat is converted into electricity. So we do have two spacecraft that won't be harmed by a dust storm like this. The problem with that is you can't depend on that because, as you might imagine, the world regulates the use of plutonium very carefully, and they don't give it out at any street corner. And so you have to have really good reasons for a mission to require it. So we have in the past and will continue in the future still need to use solar panels, and this is going to be an ongoing problem. And I don't have a picture of it because it's very recent, but we actually, the Mars InSight mission has actually probably been lost recently for the same reason. I mentioned earlier, it landed in a site where there's no wind or very little wind and no dust devils, I should say it that way. Because of that, the solar panels never cleared off the dust. And the last set of images we got, it was able to take a selfie. The solar panels are just like brown. They don't look like solar panels anymore. So it lost all its power. And so that mission's over. So where do we go from here? If you're someone like me, you want to figure out what's going on with these storms. You want to put all the pieces I've given you today and try to put it together for a complete story. What really drives the formation of these dust storms and the evolution of these dust storms? And I ultimately want to see, does it help explain what's going on Earth? Because as the Earth is slowly warming up, unfortunately, due to climate change, and due to desertification in different parts of the world where over farming has led to the expanding of the desert, we are getting actually much more dust lifted into the atmosphere. And we are going to see more dust storms around on Earth. If we could learn from Mars to understand what's going on Earth, that would be really helpful. What we need to do, however, is we probably need some new missions to Mars specifically to look at the details of how dust actually gets lifted into the atmosphere. We've never had a dedicated mission to do that. So earlier, Brian, in the introduction, for those of you who are lucky enough to hear it, heard that I'm in town because we had a workshop this week. And that workshop's goal is actually to discuss potential missions that we could probably propose to NASA to try to get the kind of data we want. And one of the cool things we did is we're trying to really get down in the nitty gritty and move beyond just big conceptual ideas, but actually start building prototypes of the type of mission we want. So we went out to the Bruneau Dunes, which is, I don't know which direction from here, but about an hour from Boise. And we went out to the Bruneau Dunes, and one of our colleagues from the Naval Research Lab, she and her team set up this contraption, which probably looks a little crazy, but I'll explain it. What this is these struts are attempting to simulate the bottom shell of a lander. So if you imagine like the nose cone of a rocket but now flip it upside down. That's what a hard lander would look like. You get this little shell, you come flying down in the atmosphere, and you crash land on the surface. So imagine if there's connecting these bars was more material. Then in the middle is your actual spacecraft. And what we were doing out in the desert is she had built up a spacecraft with some little bit of capabilities. It could spin around, it could move some things around, but then she put up a whole bunch of weather and dust and other instrumentation here to simulate a potential mission where we would go to Mars to try to observe saltation, observe dust devils, and measure them in more detail to understand who's contributing what to the formation of dust storms on Mars. So it's kind of exciting. We had a whole bunch of people out, and it was a very hands-on opportunity that was sponsored by Boise State, where we got to get out there, debate, argue what's the best way to do this, because we were trying to move forward with some ideas that we could give to NASA. But it's kind of cool that we could use these dunes out here, because they make for what we call a nice analog field site, a site that has, it's not Mars. This is not Mars. There's vegetation. It's definitely not Mars, but it has features like Mars. It's got sand all over the place, dust and dunes. That's very Mars-like. So it lets us test out ideas in an environment that is somewhat analogous to where we might want to go. So this is the first of many meetings. We're hoping to be working on this for the next, say, a few years, and hopefully after that, start proposing ideas to NASA to actually fly. But it's kind of exciting that we were able to come out here and start testing these ideas in a very tactile way. All right. So I'll just finish up here. Hopefully I gave you a little taste of what Mars dust storms look like, gave a feel for why I think they're really cool and are exciting. But I also want to emphasize that what I find fun, though frustrating sometimes, is that we still don't know a lot about them. And we want to understand when and where they form, how they evolve, right? So one of the challenges of these spacecraft missions is we don't have what's called a geostationary spacecraft in the orbit around Mars. On Earth, we have these great GOES satellites. They're in what's called a geostationary orbit. It's an orbit that tracks the surface of the Earth. So it looks at one spot all the time, right? There's one basically over Denver, and it takes an image of North America and just consistently takes an image of North America. So you get to see the evolution of storms. You see the results from these spacecraft all the time in the news when they're showing you weather. We don't have something like that on Mars. So we have large gaps in our observations. You probably noticed I had to stitch together with gaps, images and stuff like that, right? So we're looking forward. Some people have ideas to do geostationary satellites at Mars. That would be really cool. Would fill in the missing pieces so that we can understand the evolution of these storms. And then, of course, like I mentioned, we want to land on the surface and fill in that part of it. Understand how the dust even gets up there and pumped into the atmosphere. And then also for future exploration, what I mean here is even missions not studying storms and missions with humans. How do we build spacecraft and habitats that can survive this environment? Well, one of the ways that we need to do that is we need to understand it more. We've never measured directly the dust particles in the air, so we actually don't know their size distribution directly. We have ways of inferring that information, but we don't have the direct information. If you're an engineer designing a habitat for future astronauts, and you're trying to figure out how to design the seals so it keeps dust out, you need to know more about the shape and size of these particles. So that's one of the side benefits of the research you want to do, is to help that kind of future exploration. And that is everything I have. So thank you very much.
All right. I'd love to have some questions, and as you ask questions, be sure to repeat it so the folks online can hear the question. And I'm monitoring the chat here, so please, questions. Yeah, right here.
What was the name of the one theory?
Saltation.
Saltation. So could a proponent of the saltation theory argue that that one is more likely than the dust devils? Because it seems like a front moving through would, you'd have to have a lot of dust devils.
So you're asking,
much into the air.
So you're asking about the two theories for putting dust in the atmosphere, and for the saltation theory, could proponents of the saltation theory have a strong argument that it's more likely to be putting dust in the atmosphere? Not only could they,
A lot of
yeah,
this is supposed to be.
not only could they do. So most definitely, one of the arguments for saltation is The planet is windy. There seems to be dust everywhere. There's probably saltation happening all the time. It's an open question. The counter argument could be, however, and this is where we don't understand, like if you put a lot of dust in the air in a large region, is that the way you get it to turn into a storm? Or do you need to put a lot of dust in a more localized region? If it's the latter, then maybe pumping dust up in the atmosphere with dust devils might be a better way to do it, because they're like a more focused beam of dust out of the ground. But again, we don't know for sure. So that's why the group of us were out there debating how we go out there and measure that.
Yeah, a spaceship comes to Mars,
Mhm.
takes it to space. So when it lands on Mars, the dust is a different kind of danger to the seals on the ship that just made it all the way to space.
Well, okay, so a robotic spacecraft, most of the time, the issue isn't seals. The issue is covering your solar panels with dust and not getting any power anymore. Or lubricants can be an issue as well if you have motors. And you might go, well, wait a minute, doesn't the lubricants have problem in the vacuum of space on the way there? They do, but you're only flying to Mars for 6 months, 9 months or so. But now you sit on Mars for 2 years. At the end of that 2 or 3 years, you start having problems. For humans, it's different. You're going to send your habitat down out there. You design the spacecraft to get to Mars one way, but then you land and you go into the back of your spacecraft, start pulling out your equipment and building your habitat. Now you're building a habitat in a different way. How do you build that in a way that you can handle the dust? So now you're talking about building something that didn't fly through space. It was just cargo. So.
We have a question online here.
Yes. So the question is, the dust sharp or smooth? Would it abrade the robots over time? That's a great question. I don't know. Right now, the way we usually try to derive the shape of the particles is you have a little camera that looks up at the sky, and as the sky darkens, you try to use some models and some information we have from Earth, and you try to sort of derive an effective size of the dust particles. But you're not really measuring the dust particles directly. So you don't know if they're circular or if they're long little, like narrow little needles. And we do get particles like that braiding off of rocks, right? So we don't actually know how sharp or not they are. I personally have an instrument I've been developing that would actually figure this out, and I would love to know, but we don't know. And I can say this much: I don't think we've seen much abrasion on the robots so far, but abrasion is a slow process. So what the robots look 30, 40 years from now, if we send astronauts out there, that might, if I don't get this in my instrument before then, that might be the only way we'll find out how sharp they are. But so far we haven't been there long enough and haven't gone back to the same spot enough to answer that question.
Any plan to put a lander in space with a residual and seasonal polar cap?
So the question is, would we want to put the lander where we have that residual polar cap that's seasonal, that comes and goes? We would love to do that. People are trying to make plans to do that. The biggest challenge is that when the amount of CO2 that gets deposited when winter comes, so say you landed in the polar region, it's kind of clear, it's summertime, you're like, this is a nice spot, I like it here. Winter comes, the CO2 starts depositing. You can get 1 to 2 meters of CO2 ice, and it starts crushing your spacecraft. So we did have a spacecraft that went to a high latitude in the north called Phoenix. It landed in a region where it was right near the poles, not in the poles, but close, in a region where like there was actually ice underground, so it would dig and get ice, but it had a short lifetime, precisely because once the winter came and the CO2 ice came along, deposit on it, it actually, so the Phoenix had 2 arms that stuck out, and you imagine where my hands are were solar panels. Those arms were basically snapped right off. And we see this in images later from the high-rise camera. So that's the biggest challenge. Now, people have some fun ideas to get around this. What if we had like giant heaters to keep the spacecraft hot so the ice doesn't collect on it? Or what if we design it like super sturdy, almost like a submarine, but a submarine for sub ice or something like that, so that the ice would just deposit on it and the spacecraft would hibernate and come back out. people are looking at these ideas, but they haven't gone past the idea phase. There's no mission with funding to try to do this yet. But it'd be cool.
So you were just talking about how the depth of the ice.
Mhm.
How much does it expand this way?
You mean horizontally across the
Yeah,
land?
like, how
Oh,
much larger is the?
when I had to do my thesis defense, I used to remember that number. I don't.
have to be exact.
I don't remember, but it is hundreds of kilometers. The cap gets as low as like 85-degree north and stretches down to like 70 or maybe even 65. Yeah, it's quite a bit. Yeah.
So it's continents, I mean, it's continent size, you know. expansion.
Yeah,
Yeah.
so I mean, where you would land it to avoid the ice deposition.
Yeah, it can be very limiting. It can be very limiting. Yeah.
Yeah.
The biggest limitation though right now is it's just expensive to land where it's cold because motors don't work as well when it's cold. So we tend to land, plus or minus 20 degrees from the equator because of that. But there's a lot of us who would like to do what the gentleman in the back was suggesting and go north, my son, kind of thing.
There's different types and maybe different degrees and intensities of change there.
Well, and what's interesting is many of us think that the ice caps, the permanent part of the ice cap, actually records long-term changes in the climate because Mars's atmosphere, Mars planet, the planet oscillates a lot more than Earth. Earth wobbles a little bit, but the moon right there and its gravity sort of keeps it under control. Mars oscillates quite a bit. Right now it has a tilt of 25 degrees, but it goes as low as 0 and it can go as high as like 60 degrees. And so we think that in doing that, that means ice is moving around a lot. And every time it moves around, it leaves a dust lag. And so there might be a record in those polar caps of that history. So we could do what we do like in Antarctica, where we drill down, get these cores and get the history. We would love to do that. There's a whole group who are obsessed about drilling. I think there's even some people at Blue Origins, the rocket company, who are working on it as well. Gentleman down here.
What kind of velocities are we getting storms in? Are we related to something that we know, like a sandblaster versus household fan?
The question was, what are the kind of velocities we get in these storms? Interestingly enough, the storm speeds are very similar to what we get on Earth. So the average wind speed on Mars is roughly between 0 and 30-ish miles per hour. I think I have that right. I'm gonna have to convert from meters per second in my head. But the storm speeds are like roughly what you get in a thunderstorm or even a hurricane. And I didn't have time to talk about it today, but one of the older ideas about how dust storms work is what's called the dusty hurricane model, where some people in the 70s proposed that the same physics that drive hurricanes drives these dust storms. And part of the reason they proposed that is the wind speeds are comparable. The planet is smaller, but because the rotation rate on Mars is similar to Earth, it's only about a 40-minute difference, the length of the day on Mars compared to Earth. Because of that rotation, and rotation has strong control on the strength of storms, the storms end up being very similar in wind speed strength. The difference is the atmosphere is thinner, so the amount of momentum that gets moved around is a lot less. It pushes against you less, but the wind speeds are comparable. So I don't know what a sandblaster wind speed is, but if you think of a recent thunderstorm that was kind of crazy and had those really strong winds, you're in the right ballpark. Any more in here?
I think so. Yeah, go ahead.
I guess I'd ask, I've been lucky or unlucky, depending on how you see it, enough to have experienced dust storms in the Sahara in Egypt. And what struck me was people locally they kind of knew when these were coming, and they even had an unofficial name for it, which meant the 50, the Hamsin, because they knew kind of how long these things would last. I'm curious, have we definitely ruled out the trigger mechanisms for things like large dust storms in the Sahara and the Gobi? And can we semi-definitively say that's not what causes them on Mars?
The question is, have we ruled out? The question is, we know how dust storms form in the Sahara and the Mojave and other places. Can we rule out that that's different on Mars or not? I don't think so. I think there's all likelihood some relationship. I will point out that I've been out in Iceland for a field campaign once, and there's a lot of dust lifting going on there, driven by I saw both saltation and dust devils. And they periodically get little dust storms coming off of Iceland that then the dust then flies around the polar region, dumps all over Canada and Siberia. And what I saw there were phenomena that looked very similar to what we see on Mars. I'm not as familiar with what goes on in Sahara and Gobi. It's not an area I've ever studied, but I feel like I can say that there's a good chance that the fundamental physics are the same. The questions will be which ones are more important. And the other difference is on Earth, the rain and the water clouds end up scavenging a lot of the dust. Water uses dust as a nuclei to condense onto. And that leads to different dynamics ultimately, because you don't get that on Mars. It's probably limiting us from having global dust storms, because before we have a chance to have a global dust storm on Earth, the water vapor grabs onto the dust and uses it to start building water droplets. So, one more. All right. Oh, right. So basically the question online is the dust size on Earth comparable to the size on Mars? I said it was the peak size on Mars is about a micron. It's actually very similar in size. I think the peak might be closer to 10 microns on Earth, but it's not a fundamentally different size. What is different is dust on Earth. The word dust can be a little bit aggravating because it's not a precise scientific term. Dust on Earth can actually be made of other things. So on Mars, the dust is mostly what we call basaltic minerals. So a basalt is something that comes out of volcanism. Mars's surface is mostly basaltic, so that's what got eroded away, is this leftover volcanic material. On Earth, you have other things that are contributing to dust besides basaltic materials, including, and this is a little disgusting, so I apologize, but the skin off your body. So when you talk about dust, and if we talked about dust in this room, most of the dust in this room is probably skin cells that have come off of people who've been in here before. So it gets a little confusing trying to compare the sizes, because you're not comparing the same thing. But they're ultimately not that far off from each other.
Great. Yeah. Other questions in the room? Yeah, that good.
So, in the middle of a global storm with a lander that's in the middle of it, the highest surface speed would be about 30 miles an hour.
Oh, no, the highest surface speed, depending on where it is. So these global dust storms, there's so much to talk about. I didn't get to everything today. They have actually sort of cores scattered in them of excess of upwelling. So basically, you can also imagine you have dust everywhere, but there's only special regions on Mars that are pumping the dust up there to maintain the global dust storm. And actually, they're pumping them so much that we recently discovered they're actually pushing water from the surface all the way to the top of the atmosphere and escaping. But so what that means is, depending on where you went in, you could actually be encountering wind speeds closer to 100 meters per second, which I don't remember what that is in miles per hour. Do you? 200 miles per hour. Yeah, so hurricane force. But you might land in another spot where that's not the issue, because you're not hitting one of those cores. So you get the whole range. I didn't mention this either. I'm starting to remember all these things. Again, I could talk another hour or two on this. There are preferential areas where it looks like dust storms start. So source regions for dust storms, and that's where you'll get your most vigorous uplifting. There's also preferential areas where it looks like all the sand ends up, and then the dust ends up after the storm's over. Those two places are not the same, and one of the mysteries is, how does the dust get back from the sink to the source region? Because it does look like it resets itself. So and one of the ideas is that the dust devils do that. So there's a lot of weird things going on here that we don't have enough observations to really understand yet.
Great. Well, let's give Dr. Soto another round of applause. Mic here.
Oh, sure.
And those of you online, thanks very much for joining us. Again, we'll host the next event August 5th, 7:30 p.m. here. I'm afraid we're not going to be able to go up to the observatory tonight. As I said earlier, we're short staffed, so we can't actually bring folks up. But join us in August. Hopefully we'll be able to get up to the observatory then. Thanks very much. Have a good weekend. Stay safe. Thanks to everyone online. We'll see you.